So NASA just picked up something absolutely wild from 3I/Atlas today, and honestly, nobody knows what the hell to make of it yet. For weeks, we've all been tracking this thing, and yeah, it's been strange, unpredictable, even unnerving at times, but at least there was a rhythm. At least we could point at the data and say, okay, we see the pattern, we kind of understand what's happening here, and so the patients have responded. They've been easier, but today's flash blew that false sense of understanding to pieces. It's like the comet looked straight at us and said, "You think you figured me out? Watch this." Before I get into what actually happened, if you've been following this journey with me, tracking every twist, every anomaly, every bizarre signal, make sure you're subscribed. And seriously, stick around until the end of this one, because what NASA caught today, this might be the clearest sign yet that 3I/Atlas is hiding something under its surface that no one has identified. So, here's what NASA observed. This newest batch of data wasn't supposed to be special, just routine monitoring. Same instruments, same timing, same careful tracking as 3I/Atlas drifts farther from the sun. No surprises expected. They start flipping through the frames. Frame 1, normal. Frame 2, normal. Everything behaving exactly the way it should. Then frame 3 loads. And suddenly, the comet jumps in brightness. Unknown temperatures and single degrees of friction made it impossible. Something seemed to loose. The comet jumps in brightness, not the whole image, not a camera glitch, just the comet itself, lighting up like someone flipped a switch. It's not a solar flare messing with the exposure. This is something else, something tight and compact, happening right inside the inner coma of the comet. It's like someone flipped on a light switch inside that hazy shell surrounding the nucleus. And it wasn't just a one-frame glitch either. The flash stayed bright long enough to appear across multiple exposures, which means it's real. It happened. And then, just as suddenly, it collapsed right back down to its baseline brightness. No ramp up, no slow fade, just a clean spike, and then nothing. Like the comet shrugged and pretended it never happened. That's the first seriously weird part. See, when comets have outbursts, and they definitely do, they look messy. There's a signature. You can see dust and gas blasting outward over hours, frame by frame, diffusing, spreading, evolving. It's gradual. It behaves like physics. But this didn't behave at all. The flash didn't spread, it didn't smear, it didn't evolve. It just snapped on and snapped off, like a controlled emission, not a natural event. So of course the scientists did what scientists always do. They tried to kill the anomaly. They tried to prove it wasn't real. They checked for cosmic rays hitting the detector. Those can fake bright flashes. They checked for a satellite drifting through the frame. They checked for bad pixels, guiding errors, anything that could cause a sudden spike of light exactly where the comet sits. One by one, every explanation failed. Nothing matched the signature of what they saw. And the brightening? It wasn't random. It wasn't offset. It was centered perfectly on 3I/Atlas itself. The brightening didn't drift randomly across the frame. It moved exactly with the comet's own motion across the sky. And the surrounding star field? Perfectly steady. Nothing else shifted, nothing else flickered. So there's only one conclusion left. The flash came from the comet itself. This was real activity. And this is where things take a turn. The team did something clever. They stacked the images and ran a difference subtraction, basically subtracting the normal 3I/Atlas from flash mode 3I/Atlas to isolate whatever produced the extra light. What popped out of that analysis was unexpected. The extra light wasn't evenly spread across the coma like a normal outburst. Instead, it was concentrated along a thin, bright axis. Slightly offset from the direction of the main tail, it starts to expand. Pressure builds. The trapped gas pushes harder and harder against the crust above it, until the crust reaches its limit, and then, crack, a sudden rupture, a violent jet of material blasting into space. That would perfectly explain why the brightening appears as a narrow beam. It explains the suddenness, the clean on-off behavior, the tight geometry. And it might also explain something the tracking teams noticed afterward. Because this flash wasn't just a visual anomaly, it left physical fingerprints. Right after the event, the orbital calculation team started picking up on something subtle but real. a tiny change in the comet's residuals. Here's what that means. When you calculate where the comet should be, based only on gravity from the sun, the planets, the usual forces, and then compare that to where it actually is after adding the new data, there's a small mismatch, a slight offset, because when the team measured how much the brightness jumped, and more importantly, how fast it jumped, the numbers were insane. To create a flash that dramatic that quickly, the vent would have had to blast out a massive amount of material in a burst measured in minutes, not hours. That's extremely fast for comet activity. And it points to one thing above everything else: pressure. Something inside 3I/Atlas was bottling gas faster than it could leak out. That pressure kept building and building until whatever was sealing it finally failed, catastrophically. Think about it like this. Deep inside the comet, there could be an ancient pocket of volatile ice, something that's been sealed away for billions of years, completely dormant. Then 3I/Atlas swings through our solar system, hits the right temperature, and that ice finally crosses a critical threshold. It starts to expand. Pressure builds. The trapped gas pushes harder and harder against the crust above it, until the crust reaches its limit, and then, crack, a sudden rupture, a violent jet of material blasting into space. That would perfectly explain why the brightening appears as a narrow beam. It explains the suddenness, the clean on-off behavior, the tight geometry. And it might also explain something the tracking teams noticed afterward. Because this flash wasn't just a visual anomaly, it left physical fingerprints. Right after the event, the orbital calculation team started picking up on something subtle but real: a tiny change in the comet's residuals. Here's what that means. When you calculate where the comet should be, based only on gravity from the sun, the planets, the usual forces, and then compare that to where it actually is after adding the new data, there's a small mismatch, a slight offset, tiny, invisible from Earth, but big enough that the high-precision orbital software immediately flagged it. Something pushed this object. Something gave 3I/Atlas a little shove. And that is exactly what you'd expect if a one-sided, high-energy jet fired off the nucleus for just a few minutes. 3I/Atlas basically fired a tiny thruster on one side and gave itself a measurable push. But here's the part that's really messing with people, the part the teams keep staring at because it refuses to make sense. When you actually run the physics on this event, the thruster was too efficient. Based on how bright the flash was, based on how much gas and dust a normal comet would need to eject to produce that glow, the resulting force on the comet should have been modest. Noticeable, sure, but not anything dramatic, except the orbital shift suggests a stronger push than the brightness data should allow. In simple terms, the math doesn't add up. So now scientists are left with two explanations, and both of them are uncomfortable. Possibility 1. The material was ejected at far higher velocities than current models say is possible. That would mean our understanding of how pressure builds inside fractures, how gas accelerates through vents, and how energy is stored beneath the surface of an interstellar comet is fundamentally incomplete. Something about 3I/Atlas is allowing gas to accelerate with an efficiency that doesn't appear in any comet we've previously studied. If this is true, then 3I/Atlas isn't just unusual, it's rewriting comet physics. Possibility 2. We're massively underestimating how much material the comet expelled. If the flash released more mass than we think, that would change everything. It would mean the comet's internal structure is weaker, more hollow or more fragmented than assumed. And if it can shed chunks this easily, then 3I/Atlas may be far more unstable than anyone realized. It would mean rethinking its density, its layering, its internal stresses, basically its entire anatomy. Either way, the implications aren't small. And here's the part people keep forgetting. This isn't a homegrown comet. This isn't some chunk of ice from our Oort cloud that's been looping around the sun since the dinosaurs. 3I/Atlas is interstellar. It was born around a completely different star in a completely different environment under completely different conditions. Its chemistry is different. Its history is different. Its internal pressures, fractures, volatiles, everything about it is alien compared to what we're used to modeling. So when something about it defies the numbers, that might not be a glitch. It might simply be the first time we're seeing how a comet from another star system actually behaves. This object has been drifting between the stars for billions of years. Its crust isn't like the soft, crumbly surfaces of our local comets. It's harder, denser, reworked by ages of cosmic radiation. The outer layers have been chemically altered, compacted, and reshaped by conditions we've never replicated in any Earth laboratory. So when a vent fails on 3I/Atlas, when pressure finally breaks through and material erupts, it's no surprise that it doesn't behave like the outbursts we see from comets born in our own solar system. The physics might be similar, but the details, the dynamics, the limits, they could be completely different in ways we're only now beginning to understand. And that's exactly why this flash matters. This is a direct window into how an interstellar comet stores energy, traps volatiles, and releases pressure. It's a real-time experiment playing out in front of our telescopes, one that lets us infer what's happening beneath the surface. What is this comet actually made of? How is it layered? How does it react when it's heated, stressed, or cracked open? And the thing is, this flash isn't happening in isolation. It's part of a pattern, one that's starting to look a little unsettling. First, we saw jets shooting off in directions that made no sense based on standard solar heating models. Then, the coma started reshaping itself far faster than any simulation predicted. Then, we began picking up small but persistent non-gravitational forces, little nudges in the comet's motion. They kept shifting as different parts of the surface became active. One anomaly is interesting. 2 is curious. 3 starts to become a signal. And now this flash, this is the loudest signal yet. And now we've captured this discrete, measurable flash, like a single heartbeat, a heartbeat strong enough to physically nudge the entire comet. So the obvious question becomes, what happens next? If this was a one-off event, a single rupture, then it's a priceless clue, something we can analyze, simulate, and use to decode the internal mechanics of this interstellar object. But if it happens again, from the same region, then it stops being a clue and becomes a cycle, a repeating pulse, a rhythm. And rhythms tell us far more about the physics driving them. And if we start seeing flashes from other regions, places that have never shown activity before, then we might be witnessing 3I/Atlas entering an entirely new phase of its lifespan, a phase where its ancient, radiation-hardened crust is beginning to fail in stages as the comet slingshots back out of the solar system, multiple weak points giving way one after another. But there's a more dramatic possibility, one the scientists aren't eager to say out loud yet. I'll say it because it's real. A sequence of flashes like this, especially if they start coming faster and from multiple spots, can be an early warning sign of fragmentation. If enough internal stress builds up, if enough vents rupture in rapid succession, the comet doesn't just keep flashing. At some point, it cracks, it splinters, it breaks apart. We've seen this happen before with other comets. Sometimes the structural integrity just gives out, and the nucleus splits into multiple pieces. Right now, NASA's official wording is cautious. They're calling it a transient brightening event, a flash that appears to originate from the comet itself. Very controlled, very conservative language. But unofficially, everyone working on this object is on alert. Eyes are locked onto the data streams, because the next flash, if it comes, changes everything. If the light curve starts showing repeating spikes, or if the inner coma splits into multiple bright cores instead of one, that's when the narrative flips. It goes from, we caught an interesting flash from an interstellar visitor, to, we are watching an interstellar object come apart in real time. Imagine that, a breakup event happening right in front of our telescopes, a fragmenting body that has spent billions of years traveling between the stars. Until or unless that happens, what we have right now is priceless. Our first clean, undeniable glimpse of just how violent things can get inside a comet that didn't form here. The forces inside this thing are powerful, the pressures are extreme, and the energy releases are sudden, sharp, and dramatic. This isn't a gentle, predictable process at all. NASA just captured a brand new flash from 3I/Atlas, a real one, a strong one that actually moved the comet. And if the past few weeks have taught us anything about this interstellar traveler, it's that this probably isn't the last surprise it has waiting for us. We're along for the ride now, and honestly, I can't wait to see what happens next.